doors in your mind. The doors of perception. Open the doors in your mind and see the world for what it really is.
Have you ever wondered why our cars can't run forever on a liter of gas? Why we need to keep paying for energy to heat our homes? Why there are so many living things on Earth, and why they've become increasingly complex over time? And why does time always run forward, but never back? The answer to all these questions lies in a powerful, yet widely misunderstood idea: entropy. Even those who have heard of entropy are often totally confused about what it actually is, and this includes scientists.
Entropy is the most abused word in the English language or something like that. And there is a real problem with that. Some of them just use these words interchangeably and without any qualification or distinction.
Entropy is a misused and confused idea, but despite this, it is surprisingly simple.
Energy tends to spread out. Entropy quantitatively measures it. Big deal.
We call this ideas the second law of everything. In it, Ian Wilkinson strips away the misunderstandings and the myths to uncover the truth about one of the most powerful forces in the universe: entropy.
C.P. Snow, the physicist, writer, and thinker, once compared an ignorance of entropy as being equivalent to a person who thinks he is educated, having never read Shakespeare. Entropy is not some obscure, dull idea for scientists, nerds, and misguided sci-fi writers. It is the overriding principle behind life, the universe, and everything.
Still going. Long-lasting Energizer batteries keep going.
Try 5-Hour Energy. It's quick, simple, and just the thing to help you get up and moving.
Let's do this.
To help explain entropy, we must first understand energy. We all talk about energy. We eat energy snacks, guzzle energy drinks, pay energy bills, and try to use green energy. But what exactly is energy?
That's a simple but a very profound question, too.
This is Frank Lambert, Professor Emeritus at Occidental College in California, and Entropy Mythbuster.
Energy is the capacity to do things. Kinetic energy, we've all heard of that. Moving energy, a car going rapidly and anything being pushed around. When a billiard ball hits another one, or when moving molecules hit one another constantly. Those constant collisions increase when anything is heated, so the higher the temperature, the greater is the molecule's kinetic energy. Most people don't realize that a stick of wood has energy. It's potential energy in the sense that if you'd get a flame near that wood, the wood would catch fire. But what is happening is a release of its potential energy in forming new compounds.
So where did the piece of wood get its energy from?
Nature has this incredible capacity of capturing light energy, radiation, and transforming it, taking that energy, and making chemicals come together. Most everyone heard the word photosynthesis. That's what's happening. That really it's an energetic process in which the sun's energy, the radiation, is captured, and some of it, not all of it, some of it is transferred to putting little molecules together and building up cellulose and other substances in the wood, but mainly cellulose.
Where did the sun get its energy from?
Well, that's nuclear power, isn't it?
I forgot a nuclear! Ride a barrel down the falls, then cook spaghetti with meatballs. Really make your friends amazed. Nuke it with some gamma rays. Fly to Venus in a rocket, put your finger in a socket. You may suffer from exhaust, but none of that energy is ever really lost. Then why can't we make a clean machine that moves...
Energy is the capacity to do things.
Indeed, energy
can manifest itself in several forms. You already mentioned quite a few of them, like electrical energy or chemical energy.
John Schmitz works in the Netherlands and is an expert in semiconductor technology. He's the author of The Second Law of Life.
But a very common form is heat. So what often happens is that energy is transformed into heat, and once you have heat at a certain elevated temperature, then you can use that to do certain useful things, like, for instance, driving an engine or something like that. And say, often energy is converted into heat when we burn the fuel, for instance. But if we have the energy available in an electrical form, well, then you could, for instance, heat a filament of a light bulb with that, and you can generate light, for instance. Or you could indeed also propel an electrical ventilator, for instance, to move air around. So that is all possible with the different forms of energy.
Energy comes in many different forms and can be converted from one form to another. For example, the chemical energy stored in my muscles can be converted into mechanical energy to wind the crank. The crank rotates a dynamo, and the mechanical energy is turned into electrical energy. The electrical energy drives this radio, and eventually the loudspeaker converts electrical energy to mechanical energy, which moves airwaves. The moving air is transmitted to your ears, which convert mechanical energy into electrochemical energy, which eventually is interpreted by the brain as words or music.
Moves down with entropy. Defining entropy as disorder is not complete. Cause disorder as a definition doesn't cover heat. So my first definition I would now like to withdraw and offer one that fits thermodynamics' second law. First we need to understand that entropy is energy. Energy that can be used to state it more specifically.
It is clear from everyday experience that energy can be converted from one form to another. However, it's not obvious that energy cannot be created or destroyed. Energy cannot be used up. This seems very odd, especially when you come to pay your electricity bill or fill up your car with gas. Despite all financial evidence to the contrary, however, none of the electrical or chemical energy has actually been used up. It has simply been turned into a different form. One of the first people to demonstrate this was James Prescott Joule in 1845.
Joule had this box, and in the box he had a fluid with a paddle wheel, and the box was sealed so that heat couldn't get out of it, and a thermometer coming out of the top so he could measure the temperature in the water.
This is entropy theorist Rod Swenson of the University of Connecticut.
Then he had a weight on a pulley attached to the outside of the box and had the weight elevated. So again, a potential similar to the water at the top of the waterfall or heat at the top of a gradient. When he took the constraint away, and then spontaneously, because nature acts spontaneously to minimize potentials, the weight falls, as anybody would expect that it would. It turns the pulley, which turns the paddle wheel, which then, by virtue of turning, that energy is then converted into heat in the water. And then the heat shows up in the thermometer at the top of the box, and you get a rise in temperature. So in that case, what he's showing is that the fall of the weight is equivalent to a given amount of heat. So you started with the weight, that's the water at the top. You ended up with the heat, that's the temperature that was in the thermometer. And the energy remained the same. The energy was conserved.
John Schmitz.
Although we do say that we use the energy, actually that is not true. You have energy, but you can never make more energy, or you never can destroy energy. So indeed, when we go back to your example of your car, and you burn the fuel and so you generate heat, this chemical energy is transformed into heat. Part of that heat is transformed into, to do work, to propel your car. But the total amount of energy before or after the event is exactly the same. The only difference what happened is that whereas you started with a certain amount of fuel, and you could say you had your energy concentrated in a chemical form in that fuel. Once you start burning the fuel, there are several things happening. One is that you can displace yourself to another location. Well, that's good. But at the same time, you will also generate heat, which is dispersed into the environment. And say the fuel is transformed in different chemical substances, like CO2, for instance. So what you end up with is situations, yes, you are at another location, and at the same time, the concentrated form of energy which was in the fuel has now been dispersed over a large area. So the total amount of energy before and after is exactly the same, but you have it in a completely different form.
So you're saying that energy cannot be created or destroyed, but it can be, I think you said, converted or transformed.
That's actually what happens. So every time that we say in the daily language, oh, we used electricity or we use energy, what we actually are doing is only transforming the energy in one form to the other.
Okay, the story so far. You cannot make energy and you cannot destroy it. You can only convert it from one type to another. This is the first law. Even when you think you are making energy, you're actually not. For example, making electricity from a waterfall is not creating energy. It is merely converting the potential energy of the water at the top of the waterfall into mechanical energy which drives a turbine which makes electricity. So, if I cannot make energy and I can't destroy it, then I should at least be able to keep reusing it forever and never have to refill my gas tank, pay electricity bills, or buy new batteries. Let me start with something simple to prove my theory. Here I have two wind-up music boxes. If I wind up one box, it will play music until it winds down. But if I connect the key in one box to the key in the other box using a rubber band, as the first box plays the music and winds down, the key in it will turn the key in the other music box. So, as one box winds down, the other box will be wound up. With this ingenious device, I should have music playing forever. There's clearly something wrong here. I must be missing something.
I'm worried about the kids, homie. Lisa's becoming very obsessive.
I know. And this perpetual motion machine she made today is a joke. It just keeps going faster and faster. Lisa, get in here. In this house, we obey the laws of thermodynamics.
Thermo, I would say, that is the word for heat. Mm-hmm. And the dynamics is for motion. Eh? So it really comes from, say, the science, which describes indeed how heat behaves and how it can be used to put something in motion. And it can be tracked back to the period the steam engines started to emerge. And in these steam engines, people use wood or coal to burn and to, generate then the steam, which then could be used to drive the engine, basically. And that is where you have the combination of heat, thermo, and motion dynamics.
If I really studied steam engines very carefully and I oiled them and I worked very hard at it, I should be able to build a steam engine that's perfect. I put in some wood with, let's say, 10 bits of energy in it, let's just call them energy units, I should be able to get 10 energy units out the other end if I build a really good steam engine, right?
Wrong.
Wrong?
Because
Why?
you can't... Excuse me. You can't make a perfect one. That's the trouble. You continue, and you keep going and going, and yes, it is impossible. It's you can get better and better, but you can't have a perpetual motion machine just by pushing something and starting it, and then it keeps going. Well,
why
more
not?
than that, you don't want it just to keep going. You want it to do something and give you some work.
Okay, so I cannot make a perpetual motion machine, even though the first law says that energy is not actually destroyed. Basically, the first law of thermodynamics says, I can't get something for nothing. Even so, I still don't understand why I can't just gather up the transformed energy and reuse it. After all, it's not actually been destroyed or used up, just transformed somehow.
If you look to a waterfall, the water which is on top of the waterfall can still do a lot. You can use it to drive, or to spin a wheel and generate electricity from that. Once the water has been fallen down, it is still the same amount of water, but you cannot do anything more with it because it has been at the lower level. The quality from an energetic point of view has been decreased. But there is also a second law, and that law is called the second law of thermodynamics, which is the entropy law.
Did you say entropy?
Entropy.
What is entropy?
Let me first sketch a very simple situation. Say you are, in your living room drinking a cup of tea. So the tea is hot in the beginning. You put it on your table. When you wait for, say, an hour or so, then the heat in the tea has dispersed in the living room.
Mm-hmm.
So actually, the temperature of your living room went probably up a very tiny bit, but the temperature of your cup of tea went down, and at some point in time, they will all have the same temperature. And say you can easily imagine that, say, also in this process, the total amount of energy before and after is exactly the same. So the heat in your cup of tea has just gone into the air of your living room, and that is it. Now, let me ask you a question. Did you ever observe that the opposite happened? That you put a cup of tea, which is at room temperature, on your table, and that it spontaneously would heat up. Did you ever observe that? We never see the opposite, that the cup of tea will spontaneously heat up.
Mm-hmm.
And that is the same that we know that when we always see heat flowing from hot areas, hot regions towards cold regions. That's also what we see. The opposite we never see spontaneously, at least we never see that happening. And so scientists around, say, 1850 did, of course, the same observations. But so they said, well, so we are missing something here. And then they came up with a second law, the law of entropy, which prohibits that heat flows spontaneously from a cold to a warm region.
Heat won't pass from a cooler to a hotter.
Heat won't pass from a cooler to a hotter.
You can try it if you like, but you far better not.
You can try it if you like, but you far better not.
'Cause the cold in the cooler will get hotter as a ruler.
'Cause the cold in the cooler will get hotter as a ruler.
Because the hotter body's heat will pass to the cooler.
'Cause the hotter body's heat will pass to the cooler.
Okay, nice song. But what has that got to do with the fact that I cannot reuse energy?
I think really it can be understood best if I start with the second law of thermodynamics.
This is Frank Lambert, Entropy Mythbuster.
Simply, the second law is energy of all types, the kinetic energy, or let me give some examples. Light from a flashlight or from a star, heat from a stove or from your hands, sound from a stereo. These are all different types of energy. They change from being where they started, that is the light bulb. It doesn't stay within that light bulb, that energy. It spreads out. And the same thing with a stereo. The stereo doesn't stop right at the front of that little box. but the energy changes from being localized right in this one starting place to becoming more spread out, more dispersed in space, if you don't somehow box it or keep it from spreading. Entropy, that's energy spreading out. It's the quantitative measure of how widely any amount of energy becomes spread out in a process. Energy tends to spread out. Entropy quantitatively measures it. Big deal.
Almost every living thing intuitively understands the basic laws of thermodynamics.
Rod Swenson.
They understand gradients. They live off them. They feed off them. They're basically about trying to find them and consume them and then ultimately dissipate them. And I think that there's a really deep understanding of these laws. And I think for most people, too, if you can strip away the jargon, most people, without having been taught them, understand them as a necessity for kind of living and moving about in the world. And people would say, well, why hasn't somebody figured this out before? And somebody else said more recently, well, in a certain way, it's so trivial and obvious. You can show it all day long. And once you explain it to people, that they understand that it's entirely true. And the laws of thermodynamics, entropy, and the confusion that's attached to it aside are actually very simple, very basic principles.
Again, if you take the cup of tea, you put it on the table and you do nothing, then it will cool down. I would call that for the moment a spontaneous reaction. It's more simpler to describe, I think.
So this is yet another law that in general entropy will always increase?
Yeah, so it is still the second law, but it becomes then more quantitative.
So is entropy a force? Is it driving this, or is it just the result? Is it a cause or is it an effect?
It is, I would say, a description, a measure, how concentrated energy is.
Concentrated, but you also refer to high quality.
Yeah, it's the same thing.
So something with low entropy has high quality or concentrated energy. And something with high entropy is the opposite. It has low quality or unconcentrated energy. So when we transform energy, we move down an energy gradient, just like moving down a waterfall. Although the energy itself is not destroyed, it is transformed from a concentrated, high-quality form to a less concentrated, more dispersed, low-quality kind. As we move down an energy gradient from the top of the waterfall to the bottom, the entropy increases. That is, the energy becomes more dispersed and less useful. In nature, this is a one-way process, a one-way ticket with no return. Everyone and everything is on the same downhill train, and no one can ever get off.
I'm Paul Kennedy, and this is Ideas on CBC Radio 1, on Sirius Satellite Radio Channel 159, and on cbc.ca. Today, in the second law of everything, Winnipeg broadcaster Ian Wilkinson explores the sometimes murky world of entropy, a simple but widely misunderstood idea. Fundamentally, entropy is a measure of how useful or useless energy is. But entropy has far deeper implications for life, the universe, and everything.
'Cause there's another law with which all energy must agree. Whenever it changes form, it loses quality. In other words, damn that rising entropy. It's entropy, you see, that turns finesse into mess. A palace to a pigsty, why it's simply scandalous. Energy once neat degenerates into waste heat. We must repeat, because of entropy.
If entropy is a measure of how dispersed or useless energy is, then why do lots of science textbooks and some songwriters and people in general think that entropy is all about mess and untidiness, order and disorder? An often cited example of entropy involves a deck of cards. According to this, if I take a deck of cards that are in perfect order by suit and arranged from ace to king, and then shuffle them, then I have made them more disordered and therefore increased their entropy.
Those cards, let's see. The cards were cards when you started them. You moved them to new positions. They are still the same cards. They still have the same energy with them, so there's no change in energy within them. There's no change in entropy because entropy only applies to atoms and molecules and changes involving those atoms and molecules.
This is Frank Lambert, Entropy Mythbuster. He has campaigned for many years for clarity in thinking about entropy, particularly in science. Thanks to him, at least 24 textbooks have revised their explanation of entropy.
Tell me about your playing cards now. How did they disperse energy?
Oh, I did it. I
yes,
dealt
you
them.
did.
Yeah.
You did it. It was your dispersal of energy that did that. And that's always the case, this order to disorder malarkey. It has nothing to do with genuine energy dispersal of what you're looking at. You were looking at the cards, or you were making me looking at your shuffling cards. But that's not where the energy was being changed or dispersed. It was in your muscles that was occurring. And that's true. Give me a dozen other examples, and I'll show you where they're wrong, too.
Okay, what about the basement in my house is full of junk, and it's very messy. And if I was to tidy it up and put energy into it, presumably I would therefore decrease the entropy. At the moment, it must have very high entropy because it's very disordered. And then if I tidy it up by putting energy into it, I will lower the entropy of the basement, correct?
No, but I'll comfort you. Don't bother, because after you're done with those pieces all in order, that chair and that stool and that ladder, they're going to have exactly the same energy as before. They aren't warmer. They aren't changed into other compounds. And so, in essence, what I'm saying is neatness, order, and disorder really have no place in considering entropy. Entropy is a measure of the dispersal of energy. And yes, you have suffered a considerable change in the energy in your muscles if you hadn't taken in any food, any water, anything else when you were cleaning up. But the neatness of your basement has nothing to do with entropy.
Entropy is the most abused word in the English language.
All those math problems I did, and yet all the time I never really understood what entropy was. Why was that?
Due to a sad error by a brilliant thermodynamicist, Boltzmann, 1898, at the end of a beautiful treatise on thermodynamics. He made a statement that is not correct. He said, all of the things around us are in relatively great order. Then when something happens spontaneously to them, such as this burning of a piece of wood, then they become disordered. But he was wrong.
So even Ludwig Boltzmann got it wrong. And I was completely wrong in thinking that entropy has anything to do with order and disorder, untidy rooms or shuffle cards. But I have heard people talking about the entropy of information. Surely there must be something there.
No, no. The answer is no.
This is John Schmitz, author of The Second Law of Life, a book about the implications of entropy.
Entropy is in the first place a thermodynamic concept which relies on the fact that within its system there is a free exchange of energy between the different atoms or the different substituents of that system. But there has been indeed a similar concept in the information science. And that goes as follows, the story. Around, say, 1940 or 50 or so, there was a scientist, Claude Shannon, who was studying how much information can I transmit into a communication channel. How much simultaneous phone calls can you have over one metal line, for instance. And he came up with a concept that had to do with how frequent certain letters are in such a text, like an A or a C or a Z, how many times such a letter is in the English language, for instance. And based upon that, he could come up with a measure how much information a certain page of text contains. And then he had a discussion with a friend of him, Neumann, and he was explaining what he was doing and how he would call that concept. And it appeared now that the mathematical description of that amount of information in that page was very similar to the formula Boltzmann came up with. And Newman recognized that, and so he advised Claude Shannon, his friend, he said, why don't you call it entropy? Because nobody knows what entropy is, and you will have always then an advantage in discussions about this topic. And Claude Shannon liked that story, so he called it also entropy. And from that moment on, till the day of today, there is a tremendous confusion going on in the world about entropy.
Entropy is the most abused word in the English language.
So entropy has nothing to do with information either. It's simply a measure of how dispersed energy is. Low entropy energy is so-called high quality energy, and it can be used to do work. For example, turn a water wheel, light a flashlight, or move a car. These are all examples of energy gradients, just like a waterfall. High entropy energy is low quality energy. Entropy increases whenever energy gradients are exploited. And once the energy has been transformed from high quality, low entropy, at the top of the energy gradient, to low quality, high entropy, at the bottom, it cannot be reused. This is the second law of thermodynamics. Nobody listening will be surprised to learn about the first law, that you cannot get something for nothing. But the second law makes things even more disappointing. You also can't break even.
Order from disorder is a scientific rarity. Allow me to explain it with a little bit more clarity. Did I say rarity? I meant impossibility. At least in the closed system there will always be more entropy. That's entropy, and I hope that you're all done with it. If you are, here's your membership. You done with entropy? You done with entropy? You done with entropy?
Entropy says something about the likelihood that a certain system will exist, that it will occur. I said earlier that entropy, you could see it as a measure how concentrated energy is. That's one way to look at it. You can also say entropy is a measure of how likely a certain situation will be.
So entropy is also a measure of how likely a situation will be. If this is true, then how come there are so many low entropy things around us, like plants, animals, people? According to Boltzmann's equations, all of the people on this program, and everyone listening to it, are highly improbable, and therefore shouldn't exist. There's something odd going on here. A first-class paradox. How can the second law of thermodynamics be true at the same time that the world is populated by billions of highly improbable, complex, low-entropy people, petunias, and penguins? Rod Swenson is an entropy theorist, and one of those who is working on resolving the paradox. He thinks a classic experiment shows that what Boltzmann thought was infinitely improbable does in fact occur every single time you do it.
The Baynard cell experiment in fluid dynamics You take a fluid and you heat it from below, and a viscous fluid, usually silicone oil or something like that. And at a certain steepness of the gradient, small fluctuations are amplified, and you get what are effectively convective currents. Hundreds of millions of components start moving together, just as Boltzmann said was infinitely improbable. And they eventually, over time, order themselves into really beautiful kind of hexagonal cells. But the interesting thing here is that this situation where you have components moving at the same speed in the same direction, just what Boltzmann said was infinitely improbable, it happens, not infinitely improbably, but every single time. That is, with a probability of 1. In other words, it's not improbable in the slightest. In other words, it happens opportunistically as soon as the system gets the chance. As soon as it can do it, it does do it.
2 to the power of 100,000 to 1 against and falling.
What was that? Sounds like a measurement of probability.
But why does it do that? In essence, you've just said to me that a highly improbable system has come into existence, and it seems to be, by definition, have very low entropy.
Yes, well, the internal to the thing itself, of course, it does, because it's now gone further from equilibrium. That is, the cells that form, just the way living things do and just the way it does over evolutionary time. This was really considered to be the big problem, because in fact, in the real world, this was not improbable at all. But in the thermodynamic description, at least the one due to Boltzmann, it seemed to be. Living things do not violate the second law as long as they produce enough entropy to satisfy the balance equation of the second law.
2 to the power of 75,000 to 1 against and falling.
And what does that mean? It means that, so the second law classically doesn't say anything about order or disorder or improbability of order or disorder. It only says that in real-world spontaneous processes, the total entropy must always increase. Let's say a living cell produces enough entropy to compensate for its own internal entropy reduction, so that if you draw a box around a piece of the environment where it exists and the thing itself, such that the total entropy is always a net positive, increases, then the second law, classically stated, is not violated.
Human beings are a collection of 1 trillion cells. So I wonder if the same thing applies to us.
And you are right, once the human being starts to eat and to live, it is lowering the entropy of the human being itself. But at the same time, you are producing waste and heat, and so that is expelled into this environment. So if you would make the calculation of the human being plus the system you are considering, then you will see that while the human being is capable of lowering its entropy, at the same time it is increasing the entropy of its environment. And if you sum it all up, then you will see that for that isolated system, the entropy still will increase.
That, in a nutshell, is what entropy is about. You're now done with the discount.
So there really is no paradox at all. Although living things can be complex and have low entropy, the overall entropy of the universe has increased.
I think it's also useful at this point to talk about entropy production versus entropy. And that is where we can talk about living systems being highly organized and so forth. We can talk about them being constituted by dynamic order, that they are essentially flow structures constituted by the continual turnover, the flux of their components. So they bring in resources from the outside, convert it effectively into themselves, and then put it out in a degraded form, in various forms.
So that could be, for example, eating a sandwich, digesting it, taking some of the energy and molecules from it, and then basically go into the washroom afterwards.
Yeah, and not only when you're in the washroom, but you're also maybe perspiring it out. You're, it's going. You're dissipating heat as you're moving, and all kinds of things.
So living things are always exploiting some kind of a gradient, whether it's chemical.
Absolutely.
Okay.
Right, absolutely, because they exist themselves far from equilibrium. They are non-equilibrium structures. They are flow structures.
They are far from equilibrium, or another way of saying that, if you're thinking about the way Boltzmann thought of things, aren't they highly improbable?
Yes. So let's go back to Boltzmann's notion of order. So he talked about the Newtonian mechanical worldview kind of reduce the second law to the collision of particles, basically, like billiard balls, a gas in a box. And so he talked about molecules, or the components of a thing, moving in the same speed and the same direction as being the most infinitely improbable case conceivable.
2 to the power of 50,000 to 1 against and falling.
But of course, what you see in the natural world, you see it over evolutionary time, is actually things becoming increasingly more ordered in that sense, in the dynamically ordered sense, where you have in living things that their forms are, their molecular components and so on, moving in patterned ways. And then, so according to Boltzmann, that was the most infinitely improbable case conceivable. So life was then taken to be, in evolution, to be infinitely improbable.
5 to 1 against and falling, 4 to 1 against and falling, 3 to 1, 2, 1, probability factor of 1 to 1. We have normality. I repeat, we have normality. Anything you still can't cope with is therefore your own problem.
Every time you get a transition from disorder to order, say what you do in the Baynard cell, or when you have a hurricane or a dust devil or something like that, the rate at which the entropy production occurs, or the potential is minimized, increases dramatically. The more dynamic order you have, the faster those, the faster that occurs. Look across, the 4+ billion years of evolution. It started to become obvious that life arose on the planet virtually as soon as the temperature of the planet was cool enough to keep the oceans from evaporating. In other words, as soon as it could. And if you look at kind of things that happened subsequently in the evolutionary record, like with oxygen being put in the atmosphere and the way living forms arise as soon as there's enough oxygen to allow for them, you get this feeling of this opportunistic production of order and so on.
So if I interpret what you're saying correctly, this has cosmic implications, literally, because you're saying that, or you're implying that self-organizing structures are inevitable and that eventually they would become living things. You seem to also be implying that evolution is inevitable. Is that correct?
I would say absolutely, with the only caveat that whatever happens in the end has got to be reliant on both laws and initial conditions. Certainly as long ago as when some type of bacteria learned to split a water molecule and thereby release oxygen, to build structure and then further dissipate the solar gradient, that bathes the Earth, and release oxygen into the air, which then itself became an internal potential for the planet itself, chemical potential, that then other things learned effectively to feed off of. Really the most fundamental evolutionary unit for the planet Earth is the planetary system itself. It's an evolving planet, and that it evolves essentially as a single entity on which all the rest of us, which are the smaller entities, depend. In other words, on the oxygen in the air is the easiest and simplest prima facie evidence for that, because the oxygen was put there by life itself. So it's a larger view of evolution, where natural selection sits within a broader self-organizing thermodynamic view.
So from the point of view of the cosmos, we living things, the billions of people on Earth and all the other life forms, we're actually inevitable because basically you're saying that the universe wants to reduce the cosmic gradient, right? The universe itself is a gigantic waterfall, if you like. And by having living things, even the planet Earth, if you could think of that as a living unit, it actually helps to maximize the rate of entropy production.
Yep.
Okay. So if life forms and other complex structures accelerate the rate of entropy production, then entropy is increasing now and in the future. If that is true, then logically it must have been less in the past.
As we know, time only can go forward. It's called the time arrow.
John Schmidt.
Which also has been associated, by the way, with the ever-increasing entropy. And so when we go back to the, the early start of the universe, time is zero, where you have then a minimum amount of entropy because everything was concentrated in a very concentrated area only, all the materials.
And is entropy really time? Are they the same thing?
Certainly not the same thing, but they are associated, or at least people have linked them together, let's put it like that. Why? As we say that we have the second law which says the entropy will increase. Well, when you say something will increase, you have to do at least 2 time measurements to find out whether it is increasing or not. And so then an entropy has increased, then it is impossible, as we said earlier, that say we can decrease the time because the entropy cannot decrease anymore. It has been increased and that is it. So that will put the time only in one direction. There's no direction back. That has to do with the fact that a high entropy situation is much more likely to exist than a low entropy situation.
If I recall the second law clearly, it doesn't really talk about rate. It talks about an increase in entropy.
No, exactly.
This is a critical change, a very subtle point, but critically important.
Yes.
So is this like water that will always try to find the quickest route to the lowest point in a river? Absolutely,
and it's a very good it's more than an analogy that you make, except it is an analogy because it can be broadly applied to any energy distribution. And the consequence of it, that is that the second law, as you point out, says nothing about rates. It says the entropy will be maximized, or that all natural processes go to increase the rate, increase the entropy, but it doesn't say which paths out of available paths the world will take to do it. That minimizes the potential, or equivalently maximizes the entropy at the fastest rate given the constraints. And that's roughly the statement of what we'll call the law of maximum entropy production, that the world will produce as much dynamic order as it can opportunistically.
Now, there is one other thing, is that as we go back to our cup of tea, if you leave a system just on itself, it will tend to equilibrate. So in other words, it will tend to level out these gradients. So if you wait long enough, everything will take in a position of equilibrium, meaning nothing happens anymore. No net effects are possible. And they call that, the heat death of the universe, meaning everything has become equal. All temperature differences are leveled off, and nothing anymore will happen. So that's if you wait long enough, that will happen. What is long enough? Well, 100,000 millions of years, who knows?
So it's all going to end in a Winnipeg winter.
It's very, very cold out in the woods outside. Everybody knows that the heat is essentially trying to flow out of the house. So you have a game with that. You want the heat in the house. It's trying to get out of the house on its own. It's an interesting thing because depending on how well your house is insulated or that cabin is insulated, some of it's leaking. It's going by conduction through the walls, depending on what your R rating is in your walls. Some of it's leaking maybe through the windows a little bit. somebody comes to visit or whatever, and they open the door when they come in, and everyone knows, well, you don't leave the door open. You close the door as quickly as you can, and you don't open the windows and so on. And that seems very obvious. But the point that it makes is that the heat in the cabin and the cold in the woods now creates a thermodynamic potential, a gradient, a force, that the world then will try and minimize. It'll try and bring the cabin and the woods to equilibrium, trying to even out that gradient or that minimize that potential, equivalently maximize the entropy. And what we know intuitively is that as soon as we remove a constraint on its ability to do so, that is, provide a faster path, open the door, open a window, the flows of energy from the cabin to the woods will spontaneously change themselves so as to take advantage of those opportunities. Whatever configuration you pick, the system will configure itself so as to select the assembly of paths, opportunistically to minimize that potential at the fastest rate given the constraint.
It won't just maximize entropy, it'll maximize the rate of entropy increase. That's the critical difference.
Exactly. And this becomes a physical selection principle.
Right.
And that you had basically the fecundity principle, and that is that living things are striving, in effect, in Darwin's terms, to fill the dimensions. I'll use the space-time, but it was the economy of nature. Every unoccupied or previously not so well occupied place to fill it. And that as a consequence of this, the fecundity principle, and that space-time is finite, that you had a selection on those that could fill it most effectively. This is effectively filling it at the fastest rate. The way this expands evolutionary theory or solves some of the problems that evolutionary theory previously had. And nothing of this present view really falsifies the core view of Darwinian view, that is the idea of natural selection, at all. It only makes natural selection a consequence of a deeper physical law.
At first sight, living things such as penguins, petunias, and people seem to be highly improbable. After all, they are complex and have low entropy. There seems to be a direct contradiction of the second law, which says that entropy always increases. This apparent paradox disappears when we realize that the universe destroys energy gradients at the fastest possible rate. One of the best ways to do this is to have living things destroy them for you. So life is inevitable, given the right conditions. So too is evolution. The rich variety of life on Earth can be seen as a consequence of maximum entropy production. It is the second law of everything. Billions of years from now, all the energy gradients in the universe will be used up and life will no longer be possible. In the meantime, we have entropy to thank for our very existence in such a beautiful and wonderful world.
I see trees of green, red roses too. I see them bloom for me and you, and I think to myself,
The Second Law of Everything by Ian Wilkinson. It was produced in Winnipeg by Dave Riddell. You can get an audio copy of this or most Ideas shows. To find out how, or to sign up for our online newsletter and receive details about upcoming episodes, just go to our website at cbc.ca/ideas. The executive producer of Ideas is Bernie Lucht, and I'm Paul Kennedy. Stay tuned now to CBC Radio 1 and to Sirius Satellite 159 for the hourly news.